In the previous modules and in Chapter 1 of the textbook, we looked at the atmosphere in a mostly descriptive way. We now want to lay the groundwork for a quantitative analysis of atmospheric processes. The focus of this module will be on introducing some useful terminology and notation used in atmospheric thermodynamics. This material is covered in Chapter 2 of the textbook. As an idealization, we'll often refer to the evolution of a hypothetical parcel, which can be thought of as an identifiable unit of air that can be followed around as it's transported by wind and currents. This schematic tries to convey that idea. We have the atmosphere as a whole, and then somewhere within the atmosphere we have a little batch of air that we're calling our parcel that we take from some location and just follow it as it's moved around and see what happens to it. The concept of an air, as I said, is an idealization because in reality, any unit of air we try to track will quickly disperse and mix into the surrounding atmosphere, just like a drop of ink falling into a swimming pool will get diluted and lost from view. Although it's not really possible to follow a distinct parcel around in the atmosphere, pretending that we can allows us to derive laws and relationships that work quite well for describing many atmospheric processes. In thermodynamics, it's helpful to divide everything into two parts. The system, the particular thing whose properties we're studying, and the environment, which is everything that's not part of the system. In this course, our air parcel is the system, and the rest of the atmosphere is the environment. So anytime I refer to the system, think of our air parcel that we are floating around and causing to do different things depending on the circumstances. So again, there's the system, which is our parcel of air, and the atmosphere that that parcel is found within is the environment. In thermodynamics, there's three possible types of systems. There's an open system, which exchanges both mass and energy with the environment. There's a closed system, which exchanges only energy, but not mass with the environment. Finally, there's an isolated system, which exchanges neither mass nor energy with the environment. Now, it's important to understand that these definitions must take into account how long you're watching the system. Things that might be isolated in very short time periods might be less isolated or even open if you consider very long periods of time. And the examples we'll show in a moment will help illustrate that. So here's some examples of different kinds of systems. We'll start with one very familiar to all of us, the human body. Over 1 hour, or over 1 day, or over 1,000 years, it doesn't matter, they're all open systems. The human body is always exchanging mass and energy, and even after the body dies, it's still going to be an open system in terms of interacting with the environment, both through exchanges of mass and also energy. So open, open, open over all three time scales. A sealed can of soup is a little different. Because it's sealed, it doesn't exchange mass with the environment. That is, it doesn't leak. Air doesn't get in, soup doesn't get out. And that's especially true over short time periods. But it does exchange energy with its surroundings through conduction of heat. So if you take a can of soup out of the cupboard and you put it in the refrigerator, the soup will get cold inside the can even though it's not exchanging mass. And likewise, if you drop the can of soup into a hot pot of water without opening it, the can of soup eventually gets inside. And that can occur over fairly short time scales. And so for both a 1 hour time scale and a 1 day time scale, we'll call the sealed can of soup a closed system. Now, it gets a little different if you start looking way, way out into the future, because over 1,000 years, that can is likely to rust and corrode and probably break open. You're probably not going to find a 1,000-year-old can of soup that's still completely intact and has the soup inside. So probably, after that long period of time, our closed system will become an open system. Now let's think about an inflated balloon like you'd get at a party or something, and let's assume that it has a very, very slow leak so that maybe helium or air escapes from it over a period of time. Over 1 hour, you might not notice much of a difference. And so we would call it closed on that time scale, but of course it's still exchanging heat through the surface of the balloon, and so it's not isolated. Over one day, that leak may be apparent enough that you actually can see that the balloon is losing mass, losing size, and so it becomes an open system. And of course, it's still going to be open when that balloon eventually breaks and breaks down completely in 1,000 years. The next step up is an insulated thermos bottle. These are the kinds of containers that you can put hot coffee into, seal them up, and you open it up later on the same day, and the coffee is still basically about as hot as when you put it in. Over time scales that are short, like an hour or so, you can approximate an insulated thermos bottle as being an isolated system. It doesn't exchange mass with the surroundings, and it doesn't exchange appreciable heat energy. Over a day, the coffee is going to start to cool down regardless. It won't happen very quickly, but maybe enough to be measurable, and so we might start thinking of it as a closed system if we're watching it for a full day. And of course, over 1,000 years, all bets are off. Chances of that thermos still being sealed up and intact is pretty small. Last but not least, we've got the universe. The universe encompasses everything. There is nothing outside the universe, and therefore it cannot exchange either mass or energy with anything else, by definition. So the universe would be an example of a permanently isolated system. We're going to treat our hypothetical air parcel that I mentioned a few slides ago as if it were a closed system. That is, it exchanges energy with the environment, but we're going to pretend that it does not exchange mass with the environment. That's quite a leap of faith. It's as if we were pretending that our air parcel were trapped inside a loose plastic bag that doesn't leak. I say loose because that ensures that the pressure is the same both inside and out, and we're saying that it's non-leaking so that we don't have to worry about mass exchanges. The reality is that that's pretty much a fiction. Real air parcels are open systems because they mix with the environment, they get diluted, they spread out, but we have to make the simplifying assumption to be even able to do any serious analysis on what happens with air as it moves around. So now we're going to talk about working with system variables. And this requires us to introduce some definitions that may seem a little unfamiliar to you at first, but they will help us to be very clear in how we describe things as we go along. We'll also introduce some mathematical notation eventually that helps clarify some of this. So there's two ways to describe what's happening to our air parcel, our system that we're following around through the environment. We can talk about its state at a particular point in time. We can also talk about a process that's related to its evolution over time. Those are two distinct things. Any variable related to our air parcel is either a state variable or a process variable. State variables can be defined entirely in terms of the properties of our parcel at a particular point in time. You don't need to know the parcel's history. You don't need to know where it's been. You don't need to know where it's going. You don't need to know how fast it's moving necessarily. You just need to know something about the parcel at that moment in time, independent of its history. Examples would include the temperature of the parcel, its location, its pressure, its volume, its mass, its density, its specific volume. These are all different ways of characterizing the current state of the parcel at a moment in time. Process variables describe things that are not associated with a particular state of the parcel, but rather with its evolution from one state to another. Main examples that we'll see in this course include heat added or subtracted from our system or our parcel, or mechanical work done by the parcel or on the parcel. I'll give an analogy here that may make the distinction between state variables and process variables a little clearer. At 10 a.m., imagine that you park your bike in front of the AOSS building. Its location is a state variable. Knowing where you left it doesn't depend on how it got there. At 11 a.m., you park it again, but now in front of the chemistry building. Its new location is still a state variable. It's changed, but you only need to know its location at that point in time to define its state in terms of location. The distance you rode from AOSS to chemistry between those two times is an example of a process variable. You can't know that distance simply by knowing where it was at 10 a.m. and again at 11 a.m. You have to know the particular path that was taken between the two endpoints. So graphically, we can look at it like that. There's AOSS, there's the chemistry building, and you could imagine a path that is the most direct possible path, and which is the shortest distance between the 2 points. You could also imagine maybe taking a detour to the Memorial Library, which is quite a bit out of the way, and so the path that you followed then is quite a bit longer. So the endpoints are the same in both cases, and in both cases, a state variable defines the location where the bike was parked in each case, but the path that you took to get from point A to point B, from the one building to the other, depends on the specific path that you chose to take between the two. Okay, let's try the same analogy, but now adapted to thermodynamics. At 10 a.m., a parcel of air can be found to have a temperature of 20 degrees Celsius. The parcel's temperature T at that time is a state variable. At 11 a.m., we might find that the parcel has a different temperature of 25 degrees Celsius. Again, the temperature is still a state variable even though its value has changed over that 1 hour. The heat added to the parcel as it warms by 5 degrees is a process variable. You can't know the amount of heat added by simply comparing the starting and ending temperatures. You have to know the particular path that was taken between the two endpoints. Now, when we talk about a path, we're not talking about traveling a path over campus or something. We're talking about a path in terms of the evolution of the state variables. With state variables, we can meaningfully refer to the difference between a starting and ending state. For example, the difference in temperature can be written as delta T is T2 minus T1, where T1 and T2 are the starting and ending temperatures. These are both state variables, so their values at the endpoints of a process are well defined, and we can talk about the change between the two as a meaningful quantity. We can't do the same thing with process variables like heat added, because there is no starting and ending state. Remember, an object or a system does not have heat. We can't look at a parcel of air and say it has a certain amount of heat. So we can't use it as a state variable that has a starting and ending value. So saying something like delta Q is Q2 minus Q1 is meaningless. We can't do it, we don't do it, and we won't use that kind of notation. All right, let's talk a little bit about the role of calculus in thermodynamics, because it's a very mathematical topic. The math isn't super difficult, but we have to agree on some terminology and methods. And the method that we're going to be talking about here first is the use of infinitesimal or small changes to the system. So we can talk about a very small addition of heat, which might lead to a very small change in temperature. By integrating over an infinite series of infinitesimal changes, we can find the finite or macroscopic result of those small changes. This is, of course, the essential purpose of differential and integral calculus. To avoid confusion, I will just list a few terms here that I tend to use kind of interchangeably to describe the kinds of changes we're talking about. For small changes, I might say vanishingly small, or infinitesimal, or microscopic, or differential, or incremental. In all of these cases, I'm talking about small nudges to the system that may really be too small to measure, but we want to look at what those very small changes do to the system in terms of other small changes, or small responses, I should say. Now, we can integrate all of those small changes to yield a large change, or a finite change, macroscopic or measurable change. That's usually the goal that we're actually after, is to find a macroscopic relationship between things happening to the system in one form and how it responds in other ways. So let's look at a very simple example to illustrate what we're talking about in a context that you're probably already familiar with. Velocity v is defined as the derivative of position x with respect to time. And the specific relationship that defines the velocity along that axis is that v is the derivative of x with respect to t, that is dx over dt. So velocity can be understood as the ratio of microscopic differential changes in the position dx to the corresponding microscopic or differential elapsed times dt. Note that we don't care about the exact size of dt or dx as long as they're sufficiently small. All we care about is their ratio, and that ratio is the derivative. dt and dx are called differentials. Because they have no defined magnitude or value, they're only meaningful when being compared with other differentials. Starting with a relationship like the following, we can treat the differentials on the right-hand side as things we can move around algebraically. So we can multiply both sides by dt and rearrange to get dx equals v dt. In words, a differential change in position x is equal to the current velocity v times the differential elapsed time dt. And again, the absolute size of dt doesn't matter. If it's 1 second, then the velocity times 1 second will get the change in x that occurs within a 1 second period. If dt is 2 seconds, then you expect dx to be twice as large. To investigate any real-world atmospheric process, we generally want to get from our differential expressions to valid expressions for macroscopic or large changes in our parcel. Integration is the essential step for achieving this. So there's our differential equation that we just looked at. All we got to do is integrate it. We put an integral sign on both sides. And we have to add appropriate limits. The limits of integration must match. In this case, x0 is the position of x at time t0. x1 is the position x at time t1. So if you're integrating over time on the right-hand side, then the limits of integration are going to be times. And if you're integrating over x on the left-hand side, then the upper and lower limits of integration will be the x's corresponding to the limits on the right-hand side. If we define t0 to be 0, that is, we're using t0 as our starting point, and we're saying that starting point is by definition an elapsed time of 0, then x0 is just the starting position at t equals 0. We can also make t1 an arbitrary elapsed time t since t equals 0, in which case x1 can be thought of as the function x of t. So I just make the slight translation in notation there, and so now the limits of integration reflect the fact that we're starting at time 0 for the lower limit of integration on the right-hand side, going to an arbitrary kind of variable upper limit time on the right, and then our starting x is x0 on the left, and the final x is the function of t that's the upper limit of integration on the right-hand side. Now there's a caution that I have to make here, just to be careful about things, and that is that the t appearing as a limit of integration is not the same thing as the t used as the variable of integration. That is, in this case, the dt. And the same caution applies to x. Variables of integration always disappear once the integral is evaluated. They're sometimes referred to as dummy variables because they're temporary. They're used to do the integration, but once the integration is done, those variables disappear. So, to avoid confusion, it's good practice, and I have to admit that I sometimes am not careful about this. It's good practice to use different symbols for the dummy variable of integration as contrasted with the variables that remain after the integration is done. So here's some examples. These are all three exactly the same mathematical equation, just with notational differences. Here we have the version that we just saw. Here we're using t prime and x prime as a dummy variable of integration. So on the right-hand side we see that v is a function of t prime, the variable of integration is t prime, and we're integrating from 0 to t. And so that here we're making a clear distinction between t, which is going to remain after the integration, and the variable t prime, which is integrated away and won't be present after we're done. And the same thing applies to x on the left-hand side. We've got x prime as a dummy variable integration, and x of t, in this case, as the final variable that remains. And then there's a third version here, just to show that we can do it any way we want. Here we're using the Greek letter tau as the variable of integration for time, and we're using the Greek letter psi for the variable of integration on the left-hand side. These are all basically the same equations, just with different notation. The next step, of course, is to actually evaluate the integrals. The left-hand side is easy because there's nothing inside the integral. So we immediately evaluate that to x of t minus x naught. The right-hand side requires more care because there's that v inside the integral, right? The left-hand side had nothing inside the integral. Now we've got a v inside the integral, and we have to ask ourselves a question. Is the velocity v a constant, or is it a function of time? If it's a constant, we can simply take it outside the integral, like we always do with constants. So now we've got the left-hand side that we got before, and we've got v times the integral from 0 to t of just dt prime. And that can be evaluated instantly, essentially, to give us x of t minus x naught equals vt. And if we rearrange, we now have our final and complete solution, which shows that x as a function of t is just equal to vt plus the starting position x naught. So that's the easy case. If v is not a constant, then we can't evaluate the integral without knowing the actual functional form of v of t. So here we're showing it again. We're leaving it as a function inside the integral. We can rearrange if we want, but that's as far as we can get unless we know the actual function, v of t. If we do know the function v of t, then of course we can substitute that function into the integral and perform the integration, if possible. You can't always integrate any function that you put into an integral, but in many cases you can. So for example, let's take the velocity, v of t, to be equal to a starting velocity v naught plus an acceleration a times t. So now we substitute it into the integral, and we can do the integration. I'm not going to go through all the steps here, but in the end, after some rearrangement, we find very quickly that our final and complete solution for x of t is that it's equal to 1/2 times the acceleration times t squared plus v naught times t plus x naught. No differentials, no integrals. When you're done solving the problem, you've gotten rid of the integrals, and you've gotten rid of the differentials, and you have a nice, clean, functional expression for the thing you were trying to solve for. All right, well, that worked for a very simple differential equation involving the relationship between velocity and position. Let's consider a more abstract or general approach to first-order linear differential equations. The first thing we have to do generally is something called separation of variables. Once you've separated variables, integrate both sides, supplying appropriate limits of integration. And finally, you'll usually have to solve algebraically for the function that you're after. I'm not going to talk about steps 2 and 3 because those are just basic calculus and algebra, but I will talk briefly about the separation of variables. Assume that you're given a differential equation involving the variables x and y. In a different context, the variables might be temperature and pressure, or they might be density and something else. But in this case, we're just going to call them x and y for the sake of kind of an abstract treatment of this problem. And your differential equation might look something like this. You've got dy by itself on the left-hand side, and you've got some function of both x and y followed by dx. Now, both sides of the equation there are differentials, just expressed in different ways, and we're setting them equal to each other. Basically, if you were to divide through by dx, f of x and y would tell you the ratio of a change in y to a change in x. But right now, the way we've been given the equation, everything involving x and y is on the right-hand side except for the dy on the left. So as given, we can't integrate that using the method we already looked at because the left-hand side is where you'll be integrating over y, but you still have things depending on y on the right-hand side of the equation. So what we have to do to separate variables is get everything involving y on one side and everything involving x on the other side. Any constants can stay where they are. So here again is our original differential equation. And if we're lucky, which is usually the case in this class, the function f of x and y can be broken up into the product or ratio of functions of only x and only y separately. So what that would look like is something like this. F of x and y is equal to some function g of x divided by h of y. We can then multiply through by that function of y, h of y, to get h of y dy equals g of x dx. So now we have a differential involving only x on the right-hand side and a differential involving only y on the left-hand side, and we can stick integral signs in front of both sides, supply the appropriate limits, and do the integration. To summarize the approach we're going to be using in general throughout the course is that when there are two or more variables appearing in differential equations, the first thing to do is we need to eliminate all but two. If we have three or more, we need to find other relationships that allows us to eliminate the extra variables. We want to get it down to two so that we have one for the left side and one for the right side. Then we separate the variables as we just described so that only one variable appears on each side. And finally, we integrate both sides. Now, don't worry, you're going to see examples of this as we go through the course. I'll be working some of these in class so that you see the process and understand what you have to look for. The main thing you have to really look for is ensuring that you don't leave any dependence of one variable on the wrong side. Sometimes that dependence is hidden so you don't easily see it, so you have to be careful about that. Let's now talk briefly about notation for differentials. I've introduced differentials. We've talked about integrating differentials to get macroscopic or large changes in a system, but we need to distinguish between state variables and process variables, and we're going to use distinct notation for each. So differentials of state variables might include things like differentials involving temperature or height or whatever. And for those, we'll use the standard notation that looks like this. We'll have a little d followed by the variables. We have dt, dz, dh, ds, etc. Whatever the variable is, just stick a little d in front of it, and we have a differential of a state variable. Differentials of process variables like heat and work will be indicated in a different way. We're going to use a Greek delta for that. So a differential of heat or a differential of work might be indicated by delta Q or delta W. Now, some textbooks and some other instructors may not use this notation, but I find it very handy to keep track of what's an actual state variable versus a process variable in a mathematical analysis we're doing, so that we don't make the mistake of treating one like the other. For state variables, we can write things like the following, and we'll take, for example, a state variable which is temperature and use dt, and we can simply throw an integral in front of that dt and integrate from t0 to t1, evaluate that to t1 minus t0, which in this case would be the ending and starting temperatures of our system. And if we want, we can use a shorthand like delta t to indicate that difference. Delta t would indicate a well-defined difference between a starting and ending temperature state. For process variables, there's no initial and final state. So we ditch the delta notation and the limits of integration and write things like q equals the integral of little delta q. Little delta means it's a process variable, and we're integrating that to basically look at the accumulation of added heat over the process that we're considering. Q is thus the macroscopic result of integrating a particular expression for the differential delta Q. So for example, under certain circumstances, we can write the following expression for the differential heat added to a parcel, and we'll call that differential heat delta Q, and that's an association with a differential temperature change dt. So one is a process variable and the other one is a state variable. This is a perfectly valid differential equation that applies under certain narrow circumstances. In that case, the heat added on the left is exactly proportional to the change of temperature on the right, where C is just a constant of proportionality. Integrating the equation then looks like the following. We put an integral sign in front of the delta Q, but with no limits of integration. T, on the other hand, is a state variable, so we do put limits of integration, and we're going to have a starting state T1 and an ending state T2 as the limits of integration. And once we evaluate both equations, or both integrals, we're going to wind up with the total heat added Q on the left equal to C times the change in temperature on the right. And if we want, we can simplify that change of temperature, T2 minus T1, down to a shorthand, which is just delta T. Now let's consider something which is a little bit different. Let's consider integration over a closed path. This is a point which is a little hard to explain to people who haven't dealt with this before, and I don't want to get too deep into it. But the idea here is that sometimes you want to do an integral where you're following a process in differential form over an evolution which takes you first away from your initial state to a different state, and then back to the initial state again. Let me repeat that. You're leaving your initial state, you're going to a different state, but then you continue to close the loop and come back to your initial state so that when you're all done, the state of the system is exactly what it was before. In that case, the integration over any state variable is going to be zero because the initial and final states are the same. But the integration over any associated process variable usually does not yield zero. I mean, it can under special circumstances, but generally speaking, you're not going to get zero out of that process if it's a process variable and not a state variable. So mathematically, we can indicate integration over a closed path as follows. That integral sign with the circle on it is an integration over a closed path by definition. That's how we indicate what's going on. And in this case, we're using t as a state variable, and that integral over that state variable has to be zero. If it's not zero, t is not a state variable. Now we can try the same thing with a process variable, which in this case would be q, and we're using the little delta q to indicate that it's not a state variable, rather a process variable. And that integral over a closed path usually does not equal zero. All right, let me try to make this clear with a simple example. Let's imagine that you are mountain biking on a hill, and the hill in question is depicted by this topographic map where the contours represent elevation. So the center of that hill at 840 meters, for example, is the top of the hill. That's the highest point on the hill. And 760 meters above sea level is the outer edge of the hill, and you're going to be starting at a position right there at 780 meters above sea level. From that starting point, you follow that little red path, following the arrows there. You leave the starting point, you bike around the hill for a while, and when you're done, when you're tired, you come back to that starting point, you're done, and then maybe you pack up your bike and go to your car and drive home. You can see that over that time you've changed elevation, but by the time you get back to your starting point, you're back to the same elevation you started. No matter what path you follow, if you return to your starting point, your net elevation change is always zero, because elevation is a state variable, and that state variable is back to what it was to begin with, and the change is therefore zero. Now, if you're riding on any kind of a real hill with a real bicycle, you're going to have resistance, and that resistance may be low or it may be high if you're riding over bare rock versus riding through sand or through bushes. But the fact is, you're going to do work to ride along that path. Work is not a state variable. you're probably going to be tired by the time you get back to your starting point. And the amount of work you did is going to depend on the path you took. So that's an example of how work is quite different from elevation, for example. Work is not a state variable. It depends on the path you take, whereas elevation is a state variable, and if you come back to your starting point, you're back to exactly where you were to begin with in terms of what anybody looking at your situation can say about your current state. So mathematically, one way to distinguish state variables from a process variable is to integrate over an arbitrary closed path. If the result of the integration is always zero, then by definition the variable is a state variable. Otherwise, it's a process variable. Differentials of state variables are sometimes referred to as exact differentials, including in the textbook, while those of process variables are called inexact differentials. All right, let's talk about a slight different topic now, still involving variables involved in our system or our parcel. And that is the situation in which we have variables that don't change. Either it simply does not change because of an accident of the way we set up the process, or it might not even be able to change for various reasons. It might be constrained not to change. If a variable that does not change is a state variable, we can say that it's a conserved variable, and certain variables will turn out to be conserved under certain circumstances, but not others, and we'll have plenty of opportunities to look at those cases in the future. For a variable which is known in advance to be unchanging during a process, whether it's a conserved state variable or just a process variable that for some reason is not allowed to change, the corresponding differential is basically by definition equal to zero, and you can cross it out and call it zero in any equations that involve it. Specifically, there's 4 very important special cases that you should basically memorize very soon, because we'll be referring to them often as we deal with the thermodynamics of a parcel of air. The first case is isothermal. An isothermal case is one in which there is no change in temperature in the system. And notationally, if dt appears as a differential, it's going to be equal to 0. The next case is called isochoric. That's the case where there's no change in the density or specific volume of our system. Specific volume is often called alpha in this class, and so if d alpha is equal to 0, or d rho for the density is equal to 0, then we have an isochoric system. Rho, the density, is just the reciprocal of alpha, the specific volume. The next case is isobaric. In that case, there's no change in pressure. So dP, if it's present in your equations, is equal to 0. And finally, this one is a little different because this is now not a state variable which is being kept at 0 or is not being allowed to change, but a process variable. If we have no added or subtracted heat, delta Q is equal to 0, and we call that process adiabatic. Adiabatic processes are super important in meteorology, and we'll have plenty of opportunity to look at those in more detail later on. Okay, we previously made a distinction between what we're calling system variables and process variables. Now we're going to make a very different distinction, which is also important in thermodynamics, and especially in this course. We're going to distinguish between extensive and intensive variables. So many physical variables describing a system depend on the amount of substance in the system. And examples include things like mass, volume, heat added, and work done. So in the case of mass, we might measure the amount of air we're looking at, or the amount of water we have in a basin or in a container in terms of kilograms or grams or whatever unit of mass you want to use. Or we might be talking about the volume of air in cubic meters, or the liters of the volume in liters of water or a chemical or something we have in a laboratory. We might be talking about adding a certain number of joules of heat to our system, or doing a certain amount of work in terms of joules. These are all extensive variables. Extensive variables are commonly used in a laboratory setting where you're working with a well-defined sample of something. So if you have a jar of seawater that you took as a sample and you're taking it back to the laboratory to make measurements on it, you're going to be dealing with mass and volume and so on in that very kind of discrete sense where you've got a well-defined sample. Other physical variables do not depend on the amount of substance in a system. Examples include things like density, temperature, concentration, and relative humidity. In the case of density, we're looking at the amount of mass per unit volume, in this case kilograms per meter cubed. In the case of temperature, you're simply looking at something which is a property of the substance regardless of how much of it you have. In the case of concentration, we're looking at things like moles per liter or parts per million. Again, that's a relationship or a ratio that does not depend on how much of something you have. And coming closer to home, we have relative humidity, which again doesn't depend whether you're looking outside at the air outside your house or in a small container that you've captured the air. The relative humidity can be the same in both cases. These variables are called intensive. Intensive variables are almost always preferred by scientists working with the free atmosphere, ocean, or the environment. We're not usually working with samples. We're working with a free environment. We're trying to describe the free environment. And so it makes no sense to use extensive variables that depend on the size of a specific sample. Converting an extensive variable to an intensive variable is very easy. And generally in our field, we're going to want to do that in most cases unless there's a specific reason not to. Looking at this table here, we have the extensive variable volume in meters cubed in the first line. The intensive counterpart to that is the specific volume, which we'll use alpha for in this course. And so that's meters cubed per kilogram. All we have to do is take the volume and divide by the mass, and we get from volume to volume per unit mass, which is specific volume. Likewise, heat added in joules can be turned into an intensive variable by dividing by the mass, in which case we wind up with the heat added in joules per kilogram. And then finally, we can even take mass and make it an intensive variable by dividing by volume. So dividing through by volume, we get a density. Rho is the Greek letter we use for that, and that's measured in kilograms per meter cubed. Density is just the reciprocal of specific volume, so they're both really the same thing, just expressed somewhat differently. In the first case, meters cubed per kilogram. In the second case, kilograms per meter cubed. But they're both intensive variables which describe the relationship between volume and mass. So let me wrap up with the conventions that we're going to use in this course. Except where noted, we will normally use intensive variables for everything. There's a few special cases like on homework problems where we might talk about the air in a room or something, in which case we might want to specify the mass and the volume of that room, but that will be the exception. The other convention we'll use is that, with one exception, and that's temperature, we will normally use uppercase letters for extensive variables and lowercase or Greek letters for intensive variables. To summarize, in this module we looked at the following topics. The notion of an air parcel as an idealized thermodynamic system. The definitions of open, closed, and isolated thermodynamic systems. The distinction between state variables and process variables. The definitions of four special cases of conserved or constant variables, namely isothermal, isochoric, isobaric, and adiabatic processes. Finally, the distinction between extensive and intensive variables and how to convert between them. All of the terminology and notation and general concepts that are introduced in this relatively short chapter are very fundamental to things we will do for most of the rest of the semester. So it's pretty important that you go back and make sure that you're comfortable with all of these basic ideas before we get too deep into the actual applications.